Howdy, welcome back to Space Themes. This video is on command and control within your simulation. We're using a specific example of a lunar search and rescue. So we're using, rovers and people to go searching for something on the lunar surface. So you have to be able to code within your simconfig and Python systems a method of commanding and controlling all your entities in your simulation. So that's what we're talking about in this video. I'm going to hand it over to Neil to explain it all to you, and I'll see you at the end of the video.
Hello, this is the tutorial for commanding and controlling in a lunar search and rescue scenario. So let's start from the top with the overview of the mission. And you can see it here on this page. For task one, there was an easy search involving one robot. And task two is a more difficult search, which also only requires one robot, but you'll have multiple robot entities you can control. And then the final task involves a more difficult search with multiple robots. And so the whole idea is that you'll be in control of multiple robotic entities. You'll need to create a search and rescue algorithm to find the crashed lander. And the completion criteria for task two is finding the crash site using your camera sensor pointed towards the crash site. There's also obstacles such as rocks and other robots that could hinder the robots moving around. And the crash site's in a shadow. And then for the final task, there's limited resources. You'll have to use all the robots, but only one of the robots has to end up at the crash site. Rocks will block your motion, and you'll also have to have the crash site found by the LTV with crew members on it, with enough resources to get back to rescue the crew members that were crashed at the crash site. Now I'll switch to a diagram talking some about what you can do in the scenario. So here's an example where I've made these triangle icons for the LTV entities and scout entities. There might be more robots in this, but I'm keeping a simple example for now. Now let's say you want to control all four of them at once. You could define these four different waypoints, and each robot could be commanded to go to a different one to either search for obstacles or give an initial survey of the crash site. And one thing to notice is that some robots have different parameters than others. So for example, the scout robots can move faster. They have a higher speed when driving than the LTVs. And also along different slopes, for example, uh, they might drive slower or use more power when driving up or downhill. So in this case, this scout robot was able to reach this waypoint first, and this other scout is being a little bit more careful driving down this crater, so it hasn't reached yet, and the LTVs neither have reached anything yet. And all of this information about the slope versus the power utilization and speed of each entity is in the wiki page. So I can pull that up here. If you go to this API documentation and search slope versus power or speed curves, you can find it. I want to see the speed curve, so I'll go here. So here, for example, we can see the LTV max velocity is 6 meters per second at a 0% slope grade. The Scout has a 7 meter per second max speed at a 0% slope grade. And for example, if there's a 20% slope grade, which is around a 11-degree incline, it will have a lot smaller velocity. And you can incorporate this into your Python programs through the equations on the plot. So for example, these coefficients, you'd plug this into this equation, which would be 5.6 times e to the negative 25 plus 1.4 for that decay function. And so we have this for all the different entities, and you can use that to figure out uh, in your algorithms which you'd like to go where for which entity. And so Just thinking about designing the algorithm, you might want to consider the terrain data, might want to consider the power available in each entity, and you might also want to consider searching a quadrant um, at the start, or once something is seen with a camera, you could all move all the robots to go one way. And for the final task, there's other complications with having to charge the robots and also place communication beacons. So those are extra things to think about. Um, you might lose comm if you're too far away from the communication beacons, and if you're out for too long searching around, you'll have to come back and charge, check the state of charge on your batteries, and then go out and search again. And so next I'll go into the event manager, mission manager, and entity behaviors to show you exactly how to use the Python commands to move several robots in a loop. All right, to get started with the event manager, I want to show this scenario where the crashed lunar lander has been found. So here's an example of an event triggered when the LTV over here, the camera, was pointing out and found the area of interest. In this case, it found the crashed lander. And you can see the event manager made this message pop up saying, the sim is complete. Time elapsed was 57 minutes. And at this point, the sim had stopped because this event had been triggered where the crash lander had been found. And next, I'll jump over to the mission manager, which ties into the event manager. So if we go look at the wiki here for API documentation, in this case, I'm specifically looking at the Lunar search and rescue documentation. Scroll down to these subsection links and you can click Mission Manager Functions. And here's a list of all the different commands you can use. So for example, one here is command move to coordinate, and this takes in the entity. So in this case, it could be the LTV, the scout, the trek, or anything in the simulation. And you pass in an XY coordinate as well as a task ID. And for all the commands on this page, you can see an example usage. So here, more specifically, we defined a target XY of a relative location of 100 in the X and 50 units in the Y. We plug that in here, the LTV1, and we'll name it move1. And next, let me talk more about how that ties into the event manager and the task graph. So if we go back up to the subsection links and click task graph, we can see that the task graph module is a way to organize the commands and dependencies and actually send commands to the different parts of the simulation. So what we did was just defined a command. Here's another usage of command move to coordinate. And we're plugging this into the task graph as a task and naming it task 1. And down here, we're actually adding the task. And so you can see with its logic here, first we're executing task 1. There's no dependencies for that. So this second part is blank. And then we want to send in task 2, which in this case was rotating. And there's a dependency on that. We want it to happen after task 1. So put task 2 as the first parameter. And we plugged in task 1 as the second parameter because task 2 depends on task 1. Okay. Now let's go back up here and the mission manager functions. I want to talk some about the different commands, and there's orientation commands, camera commands, and pretty much everything in this whole list explains different things. And I'll focus right now on some of the camera commands. So there is a command, camera pan, which controls how the camera is rotated. And so you can plug in an azimuth and elevation and make camera of an entity turn. And if you want to capture an image, there's a command for capturing an image. And you can plug in an exposure value, which entity's camera you want to use. And this can also be plugged into the task graph as a command, just like the previous images I showed you. Next, if you want to view those images, here's an example code of how to process the image and make it pop up in a window on the side using the Python API. So what happens is uh, you'll just copy this whole definition into your Python system. And so it's this function called process image. And you can see the example usage here where you'll take the captured image from a specific entity and process it, and that will make it show in a separate window. All right. And next, there's also entity telemetry commands, which are more related to sensor readings and getting information from each entity or robot. And this one, for example, is get current XY. You can use that to get the current position in XY coordinates for any entity. And then another useful one is get LiDAR obstacles. So this will look for obstacles within the search radius of the LiDAR of the entity. So for example, if you're looking for a rock, you could use this or any robots that might be obstacles. And it will return the relative vectors of radii and whether or not it had comms. And the specific details for each of these functions, as well as everything you can use, is down here. So for example, if you wanted to see more about get ladder obstacles, you could search that and look exactly what it returns and what it does. Uh, Other things that are useful are get state of charge, which will be used for the final task where if you see that your robot isn't moving, you might check, okay, how much capacity does it have left in the battery? And this will tell you from 0 to 1 how much is left. And you'll want to build in some logic to recharge the different entities and make sure that they get back to the station before they run out of battery. And so this is what get charging station XY is. And so you can check the state of charge and go to the charging station using the movement commands. And then once you're full, you can go on and search again. And next I want to jump into another tool. It's called Moontrek. So this is a map you can use developed by the NASA Jet Propulsion Laboratory. And essentially what you can do is you can look at the latitude and longitude in the simulation and match it up with the latitude and longitude here to view the slope map and different conditions to help plan your search and rescue task. So you might be able to see the exact slopes of a crater. And you can play around with this tool and go to different layers to look at different hill shade maps and slope maps. You can toggle visibilities like this to see exactly what you want to see. So this is something you could tie into your Python program and automate the trajectories or plan paths based on this to help with the power and speed curves based on the slope. Okay, next, let me talk about a more specific scenario. And let's go to the Space Teams platform for that. So here's the lunar surface, and here there are multiple entities placed. So if I just kind of look here quickly, there's two LTVs here, there's some scout rovers here, a truck rover, sampling rover, and excavator rover. So I'll start with talking about the lighting or the headlights and the cameras on each entity. So some entities have fixed headlights, whereas other entities have lights attached to the cameras, meaning for the LTV, for example, it just has a fixed headlight that will point in front of the LTV, no matter which way the camera is pointing. Whereas entities such as the Scout rover have a light attached to the camera. So if you pan or tilt the camera, the light will move with the camera. So refer to the wiki for exact specifications for each entity to figure out what has what in terms of lighting. Another thing I'd like to mention is that I'm currently only showing everything in this lighted region because it's easier to demonstrate for this video. But you might be searching through some dark and shadowed areas, especially when searching down slopes and within craters. So using the lights and cameras are essential, and you should incorporate strategies into your algorithm based on the lighting conditions.
Next, I'd like to talk about these communication beacons. So let's zoom into one of these over here. Okay, so communication between the entities with a mission manager depends on line of sight with these communication beacons. More simply put, the entities and robots have to be visible to the communication beacons in order to consider to have communication enabled. And if a robot doesn't have line of sight with the communication beacon, then it will be considered not within the communication system. And it will have a loss of communications. And the default entity behavior for that would be that the entity stops and then backs up until it gets back into the communication range or within line of sight of communication beacon. And then from there, it can take another command. And this is an entity behavior that can be edited if you'd like to have some sort of autonomous operations outside of the communication line of sight, but that is up to you to program. And also, these communication beacons can be picked up by the crew members on an LTV, and that is a command defined in the wiki. Then the LTV can drive to a different spot and place the communication beacon down wherever you'd like them to be. So this kind of plays into a strategy of whatever area you're searching, you might want to place communication beacon high up, or if you're searching somewhere else down here, you might place at a local high point in this area, and so on. Wherever you'd like to have line of sight communication to search an area, you should place the communication beacon that best benefits your search strategy. I'll briefly mention these other rovers and entities over here. So here's an excavator. Here's a sampling rover and a truck. And for the final task, all of these need to be used, and it's to your benefit to use all the entities because there's a large area to search, and the more robots you can have searching in parallel at the same time and working together can help you search for things and take less time, and you'll be able to find the crash site easier using more more robots working together. Next, I'm going to go over to this charging station and mention what this is used for. So the charging station, as the name implies, can charge the different entities and robots. There's a command to check the state of charge of each entity, and you should incorporate this into your code as you go, so you can make sure that none of the entities will lose all of their charge and be stuck. And in order to recharge an entity, you just have to command it to drive to the coordinates of this charging station. And you can have a function that listens or checks when the charging is complete, and then the entity can continue from there and do what you'd like it to do for your search and rescue algorithm. And then the next thing is that I'll go ahead and show you an example code of what it's like to command this LTV1 to take pictures and move around. So let's go to my example mission manager that I've written up, this Python system. And I've written some comments here, but the first thing I'm having the mission manager do is use this entity telemetry function. That's what ET stands for, to get the current XY position. So I'm saving that as XYLTV1. And here I'm defining a list of 10 different waypoints. I'm incrementing the X and Y positions just to define 10 different waypoints. Next, let me jump down to the logic I have for assigning the task graph and adding tasks to the mission manager. So here, for simplicity of reading, I've listed them all, but in your algorithm, I suggest using a loop or use a for loop and increment indices. But here I've written them out just so it's easier to understand in case you're not familiar with everything. So I'm starting with move 1, where I'm using command move to coordinate, waypoint 0. Then I'm taking a picture. Next, I'm moving to waypoint 1, taking a picture, moving to waypoint 2, taking a picture, and I've done this 7 additional more times all the way down here to move 10 and image capture 10. So this is just a very simple way to move to 10 different waypoints and take a picture at each one. You don't necessarily have to take a picture after moving each time. You might add conditional logic to only take pictures when needed. Maybe after every several waypoints, but it depends on how you define your waypoints and what you see in your images. Okay, next, let's jump back to the simulation and I'll unpause the time by pressing period to let you see how the image capture works. So let me play this forward and I'll show you camera pictures being taken and how that works. So I'm going to speed up the simulation to be 1x speed and you'll see this LTV1 driving. And I've set it up to drive to 12 different waypoints and to take a picture at each time. And when pictures are taken, they'll pop up in a separate Python window. And so you can press Alt-Enter to get out of full screen. You can drag your window to the left or right. Now you can see this camera image pop up on the right. And it's exactly what the LTV sees from the camera. And I have it drive to another waypoint and take another image. So you should see the window on the right update when a new picture is taken. So this involves using the camera capture commands and also panning the camera if you'd like, or you can have the vehicle rotate. So here's another image where you can see the LTV shadow from this perspective. So the idea is that you'll search around the whole area, keep taking pictures, and once the camera is pointing at the crash lander, that you can use these images to see what the LTV is seeing and finish the scenario. Here, just took another picture. And there's one more. So you can control these entities to do what you'd like and figure out the best way to search. And I suggest using all the robots at once to search different areas. There's plenty of entities and robots to use here. And last, I'd like to go back to documentation and show you exactly what you'd like to do and the different constraints you have. So again, the completion criteria is that you'd like to find the crash site using the camera and to avoid obstacles along the way. So for this, you might want to make a map of the obstacles before you start searching everything so that you can move more efficiently. And in the documentation here, I suggest looking through all these commands and getting familiar with them and testing them out. And if there's anything that you're not sure about how to do, we have plenty of example code here that shows you exactly how to do things. Last, don't forget to look at the different equations and the slope versus power curves to help optimize your power utilization as well as the speed And so you can see here now where the LTV is, that it's moving uphill, and it would move slower than these others that are going downhill. Okay, good luck.
Okay, that is it for this video. If you have any questions or you want to look at anything that we did, make sure to check the link on the bottom of this video that takes you to the wiki page so you can see the code and anything else that was used so you can use it for your reference while building your own command and control simulation. Thank you.